when we were doing research about you, we uncovered something called heterogeneous integration in AI chips. So, what is heterogeneous integration, and how does it impact performance and the packaging density of AI chips? This density thing being critical to building more and more powerful chips, because obviously, the more transistors you can get in a smaller space, the more powerful a chip can be.
Yeah, that's an important area, and I called it earlier in our conversation. So this is like what is more than Moore. So what dimension drives performance, or allows to scale performance beyond just making smaller transistors on a chip. This is the additional dimension driven by heterogeneous integration. And maybe let me just quickly, with a sentence, come back to the AI for AI. So we call that, we have like branded it a way that we call that materials intelligence. This is the use of artificial intelligence to drive the development of novel materials for applications in electronics. We call that materials intelligence, and this is a bit how our team works as a global R&D team, not just in a traditional way, sequentially improving properties of materials by using AI to replace experiments in order to kind of avoid unnecessary experiments, and going straight into where it really matters. Where can you really make a difference for the customer technology? How can you anticipate how a material works in a customer setup, and how does it drive the solution of their problems, and not just chemicals properties in the first glance. So this is how we drive the development of novel materials. We talk about millions of different options that need to be optimized in order to drive the performance of materials. So this just to give you the idea on how that blends into AI for AI. Second is then driving the different aspects of how our customers improve the performance of their devices. And besides shrinking the transistor, building more integrated systems, and heterogeneous integration is the important area here. You know, it started traditionally with what is called kind of a front-end process, making a transistor, and back-end was then you wire it somehow that at the end the signal gets to the outside, which is then called in a broader scheme packaging. Now there's something between these two extremes. It's called heterogeneous integration, when at the end the chip is not just one die, one single chip anymore, when you combine different chips to a system. And I refer to it in this specific example as CoWoS. These structures being built in the examples I've used. I can use different customer examples here as well. Just wanted to use one nomenclature which is pretty common in the current conversation. This is when you glue dies on top of one another in order to build memory stacks, for example, or you build a memory stack and you kind of almost glue it next to a GPU in order to shorten the transfer of data, and to make it more efficient in getting the data to the GPU. And that is called heterogeneous integration, to make that possible. And it requires, of course, technologies well advanced from what was used in packaging historically. So much smaller structure sizes, much more complicated efforts to get your heat out of the system, as one example, or to optimize power consumption. The precision required then needs different technologies, more front-end like technologies, and which makes it an area, of course, for materials innovations and for metrology innovation, as per what our company is focused on.